Hi, I'm Mark Barsamian with the Ohio University Math Department. In this video, I'll be introducing the concept of plane separation and introducing the plane separation axiom. This material is produced for Ohio University Math 3110-5110, College Geometry. The corresponding reading for this video is section 4.1, the plane separation axiom, in the book Geometry, a Metric Approach with Models by Millman Parker. The corresponding homework is this collection of, 9 exercises from section 4.1. In the previous sections, we saw that there's a notion of distance in our metric geometry that agrees with our notions about distance in drawings. In chapter 4, we're interested in other kinds of behavior of drawings. There's a typo here. Here are 4 examples of familiar behavior of drawings. Example 1, let's consider the way a drawn line, L, splits the plane of a drawing. So in this drawing we have a line L, which would be this drawn red thing. Notice a few things. Any point must be either on line L, like here, or on one side, like here, or the other side, like here. Another thing to notice is that if 2 points are on the same side of the line, then the segment that connects those 2 points is also on the same side of that line and does not intersect the line. On the other hand, if 2 points are on opposite sides of that line, then the segment that connects those 2 points intersects that line. Here's another example of behavior in drawings. In a drawing, any line that intersects a triangle at a point that's not a vertex, like this, goes on through the triangle and comes out somewhere else. In this drawing, the line continues through the triangle and comes out the other side and intersects that opposite side. Here's another behavior in drawings. Drawn triangles have an inside and an outside. And then this 4th example, in a drawing, any ray drawn from the vertex of a triangle into the interior of the triangle must come out the opposite side somewhere, intersects the opposite side and comes out. In chapter 4, we'll see the introduction of a new axiom called the plane separation axiom, abbreviated PSA, that will ensure that our axiomatic geometry will exhibit behavior analogous to the behavior of those drawings above. In order to understand the statement of the plane separation axiom, we need to first discuss the concept of a partition of a set and the concept of convex set. Here's the definition of partition of a set. These words, this set of things is a partition of set A, means this. The following 3 things are all satisfied. Each of the things in that set, A subscript 1, A subscript 2, and so on, A subscript I in general, is a non-empty subset of this set A. Also, the set A is equal to the union of all of the A subscript I. That is, this green set A can be obtained by finding the union of that whole collection of A subscript I's. And the 3rd requirement is that that collection of sets is a mutually disjoint collection. That is, if you have an A subscript I and an A subscript j, where I and j are not the same number, then the intersection of those 2 sets is the empty set. Here's some examples of partitions. This set, even integers, odd integers, is a partition of this set, the integers. So notice on the left here I have a set that contains 2 sets, the set of even integers and the set of odd integers. So we see that the set of even integers union the set of odd integers equals the set of all integers. And furthermore, notice that these 2 sets are disjoint. So every integer falls into one of these sets, either this one or this one, but not both. This set, the set consisting of positive real numbers and negative real numbers, is not a partition of the set of real numbers, because this union is not all of the real numbers. However, this set is a partition of the set of all real numbers. Every real number is either positive or negative or zero. That's the third possibility. So if I take the union of those three sets, I do get the set of all real numbers. Whereas in example B, the union is not all real numbers. The reason that the union is not all real numbers is because the union is missing the number 0. Another example of a partition of the set of real numbers is this one, the set of rational numbers and irrational numbers. Every real number is either rational or irrational. Let's go on. Another term used in the plane separation axiom is the term convex set. Here's the definition. These words, S is convex, can only be used in this setting when you have a metric geometry in the discussion and this thing S is a subset of the set script P. In other words, the symbol S denotes a set of points. What does it mean? Well, this sentence, S is convex, means the following. For every two distinct points, A and B, that are in set S, the segment AB is a subset of S. Now there's a formal quantified version, that is a version using symbols of what I just said. For all A and B in set S that are distinct points, this predicate is true. Segment AB is a subset of set S. It's often more helpful to think of the universal conditional version. So that would be this. For all A and B in the set of points, such that A is not equal to B, if A and B are elements of set S, then segment AB is a subset of set S. And it's helpful to illustrate that universal conditional statement. If A and B are distinct points in set S, then segment AB is a subset of set S. Let's go on. Now, how do we prove this set is convex? Well, the statement of convexivity is a universal statement. For all A and B in the set of points, such that A is not equal to B, blah, all that stuff is true. Well, to prove a universal statement, we have to do a general proof. So for example, in the Euclidean plane metric geometry, so remember the set of points is R2, the set of lines is the Cartesian lines, and the distance function is the Euclidean distance function. Let's define sets of points P1 and P2 in the following way. P1 is the set of all ordered pairs of real numbers such that x is greater than 3 and less than 5. Set P2 is the set of all ordered pairs such that y is greater than 3 and less than 5. The claim is that P1 and P2 are convex. So let's show that P1 is convex. Think about proof structure. To say that a set is convex means for any 2 points that are not equal to each other, if the 2 points are an element of the set, then the segment is a subset of the set. So our first statement of the proof should mention all of this stuff, and our final statement of the proof should be that. So look, there's the first statement of our proof. Suppose we have 2 points that are in set P1 and that are distinct points. Now look how this proof ends. We show that the segment is a subset of P1, and that proves that P1 is convex. That is, these 2 statements and the definition of convex tell us that P1 is convex. Now, how do we prove this? Well, if A is in set P1, then A is a point of this form where x is between 3 and 5. And B is a point of this form where xb is between 3 and 5. Now, we need to show that this segment is a subset of P1. So we have to say, well, suppose that we have a point that's on the segment. We have to show that that point is in P1. So that little proof there, that little mini proof, is how we prove that segment AB is a subset of P1. Well, let's work forward from here. To say that C is an element of that segment means, well, one of three things has to be true. Either C is equal to A, or C is equal to B, or C is between A and B. That's by this statement in the definition of segment. Now notice we have an OR statement, so that means that we can set up a proof by cases. In the first two cases, if C is equal to A or C is equal to B, then clearly C is in set P1, because A and B are each in set P1. The third case is this one. Suppose C is between A and B. Well, then the x-coordinate of C will be between the x-coordinates of A and x-coordinate of B. Now, I'm not going to go into great detail here. In the next section of the book, we'll prove this sort of thing with a little bit more mathematical precision. But the idea is the x-coordinate of C is going to be a number somewhere between 3 and 5. So that tells us that C is an element of set P1 in this case as well. So we can conclude that C is an element of P1 because it's true in every case. So that's the general style of a proof that a set is convex. Again, notice that it's a general proof. You start by saying, suppose you've got some points, not examples of points, but just some generic particular examples, so generic points. Now here there's a typo. The proof that set script P2 is convex is similar. Let's go on. Now here's a picture of set P1. This pink shaded region, which has dotted borders indicating that those vertical lines are not members of the set. That pink shaded region is the set of all ordered pairs xy such that x is greater than 3 and less than 5. A picture of set P2 is shown here. It's a picture of all points xy such that y is greater than 3 and less than 5. Let's go on and do a more abstract proof about convexivity. Example 3. Let P1 and P2 be sets of points in a metric geometry. We need to prove or disprove. If P1 and P2 are convex, then P1 intersection P2 is convex. This statement doesn't mention anything specific about the metric geometry, so the claim is actually implicitly quantified. That is, it's a universal claim about all metric geometries. So it really could be written with the quantifiers shown clearly in the following way. For every metric geometry, and for all sets P1 and P2 that are sets of points, if P1 and P2 are convex, then P1 intersection P2 is convex. So how would we prove this sort of thing? Well, this is a universal conditional statement, so we do a direct proof and observe the structure. In statement 1, we have to introduce generic elements that are described in the quantifier and in the hypothesis. So in other words, we suppose we have a metric geometry, and we suppose that we have two convex subsets of the set of points. So that's all the stuff that's mentioned in the quantifier and in the hypothesis. We have to end the proof by saying that P1 intersection P2 is convex. So that's that statement. So now we have to bridge this gap. Now, how do we do that? Well, let's think about how we have to end the proof structure of getting to this point. To prove that a set is convex, we have to suppose that we have 2 points that are in that set that are distinct points, and then somehow show that the segment that connects those points is a subset of that set. So that's a frame of statements that's necessary to show that this statement 6 is true. So we have to have this frame there in order to get to step 6. So now we've narrowed the gap in our proof. We now have to bridge this smaller gap. How do we do that? Well, notice that this statement 2 contains a defined term. P and Q are in the intersection of P1 and P2. Well, that means this. P and Q are both in P1, and P and Q are both in P2. So we've unpacked the definition of intersection, this defined term in statement 2. We unpacked it. Now let's look ahead. We want to get to this. We want to say that this segment is a subset of the intersection. Well, to get there, we have to show that the segment is a subset of P1 and the segment is a subset of P2. So we have no choice about this statement having to be there, and we have no choice about this statement having to be there. So we have now just a gap in the middle. We see there actually is no gap. We have all the statements that we need. There are no missing statements. All we have to do is provide justifications. So that's an example of proving a universal statement by doing a direct proof. Let's go on. How do we prove that a set is not convex? Well, first, let's determine the negation of the statement that the set is convex. Now here there's a typo. So to say that a set is convex means this. For all P and Q in the set S, such that P is not equal to Q, segment PQ is a subset of S. So what would be the negation of that? Well, we start by just putting the negation in front of the whole thing, and then we move the negation to the right. When we move the negation to the right, it changes this universal quantifier to an existential quantifier. Now the negation is parked in front of that old predicate. But the negation of segment PQ is a subset of S is just simply this statement. Segment PQ is not a subset of S. So the statement that a set is convex is this. For all P and Q in the set S such that P is not equal to Q, segment PQ is a subset of set S. The statement that a set is not convex is the following. There exist points P and Q in set S where P is not equal to Q such that segment PQ is not a subset of S. So observe that the statement of not convex is an existential statement. Therefore, if the goal is to prove that a set is not convex, then you have to produce an example of distinct points P and Q in the set S such that segment PQ is not a subset of set S. So here's an example of that type. Let P1 and P2 be sets of points in a metric geometry. Prove or disprove this. If P1 and P2 are convex, then the union P1 union P2 is convex. Well, as with the previous example, this claim is implicitly quantified. That is, the claim is really saying this. For all metric geometries and for all subsets of points, if both sets of points are convex, then their union is convex. Well, in fact, this statement is false. To prove that the statement is false, we need to prove that its negation is true. In order to do that, we need to first correctly write the negation. It's extremely important that you remember that the negation of a conditional statement is not another conditional statement. So a common incorrect negation is this. Students will say the negation of if A then B is if A then not B. That's incorrect. The correct negation is this. The negation of if A then B is the following. A and not B. In this negation there is no if and there is no then. So the negation of this original claim, the original claim says if P1 and P2 are convex, then P1 union P2 is convex. The negation is there exists a metric geometry such that there exists sets of points P1 and P2 such that P1 and P2 are convex and P1 union P2 is not convex. Notice again, the negation does not have an if, does not have a then. It's just an and statement. Now we see that the negation is an existential statement. There exists a metric geometry such that there exist sets of points P1 and P2 such that P1 and P2 are convex and P1 union P2 is not convex. Remember that we prove an existential statement by providing an example. So in the special case where one is disproving a universal statement by providing an example to show that the negation is true, that example is called a counterexample. So our job is to produce an example consisting of a metric geometry and two sets of points, P1 and P2, such that those two sets are convex and their union is not convex. Well, here's an example. Consider the Euclidean plane metric geometry, and these two sets defined the following way. Script P1 is that set of all ordered pairs where x is greater than 3 and less than 5, and script P2 is this set of all ordered pairs where y is greater than 3 and less than 5. Now we observed in our previous example too that those two sets are both convex. However, notice that their union is not convex. Now we need to be very clear about the claim that their union is not convex. That is, we have to provide an example of points A and B that are in the union such that segment AB is not a subset of the union. Now on this page there's a typo. We should have A equals 4, 0 and B equals 0, 4. Those points are shown on this drawing. There's point A and there's point B. We see that A is in set P1. A is in that red set. So A is in the union. And notice that B is in set P2. B is in that green set. So B is in the union. Now observe that this point 2, 2 is an element of the segment AB. But 2, 2 is not an element of the union. 2, 2 is not in this overlapping region that's the union of those stripes. So this shows that the segment AB is not a subset of that union. This segment is not a subset of that union because we can identify a point that's on the segment that is not in the union. So this demonstrates that the union of those two sets is not convex, and so it's an example of two sets that are each convex sets but whose union is not convex. Now remember, an earlier example showed that if you have two sets that are convex, their intersection is convex, and we did a general proof of that. That's always true. We can see that that's illustrated in this particular example by this. The intersection of set P1 and P2 is this shaded square that is a convex set. But the union of P1 and P2 is this cross-shaped region that's not convex. Let's go on. Finally, let's discuss the plane separation axiom. With the terminology of the partition of a set and convex set, we're now able to understand the wording of this axiom. So here's my version of the definition. These words, a metric geometry satisfies the plane separation axiom, means the following stuff. For every line L in the set of lines, there are associated two sets of points that are called half-planes, and they're denoted by these symbols, capital H subscript 1 and capital H subscript 2, or some other subscripts that indicates which one you're talking about. And those sets have these properties. First of all, these three sets, the line and those half-planes, those three sets form a partition of the set of all points. That's one property. Another property is each of the half-planes is convex. And finally, the third property is if a point A is in one of the half-planes and a point B is in the other half-plane, then segment AB intersects line L. Now before going any further, let's illustrate those. The illustration of PSA 1, the three sets, the line, half-plane 1, half-plane 2, form a partition of the set P of all points. Well, we could illustrate that with a drawing such as this. So these three sets, H1, H2, and the line, form a partition of this set of all points. Now, how do we illustrate PSA2, that each of the half-planes is convex? Well, remember that the statement of convexivity has a universal conditional statement. So I'm going to illustrate the universal conditional version of the term convex. So I'm going to draw one of those half-planes. There's a half-plane, and I'm going to draw two distinct points in that half-plane. Now I'm going to make a copy of this drawing over to the right. So the statement that half-plane H1 is convex could be illustrated by this drawing. If you have points P and Q that are distinct points that are elements of set H1, then segment PQ is a subset of H1. Finally, how do we illustrate PSA3? If A is an H1 and B is an H2, then segment AB intersects line L. Well, I'll do the same thing, making two drawings, one to illustrate the hypothesis and another drawing to illustrate the conclusion. So there's my illustration. If point A is in H1 and point B is in H2, then segment AB intersects line L. Notice the style of my drawing. On the right, I left out stuff, like I didn't show the half-planes in the second drawing. It's because the second drawing is meant to illustrate the conclusion. Segment AB intersects line L. In that sentence, segment AB intersects line L, there's no mention of half-planes. So I want to have a picture that just illustrates this, draws our attention to that. So I didn't copy this whole drawing over there on the right. I didn't put those half-planes in there to distract us. So those are illustrations of the statements in the plane separation axiom. Let's go up and look at some more terminology. There's some additional terminology. That line L that's mentioned early on in the meaning of the plane separation axiom, that line L is called the edge of half-planes H1 and H2. And these words, to say that points A and B lie on the same side of line L, that just means that they're elements of the same half-plane. So a picture like this. Those 2 points are in half-plane H1, and that means that they're on the same side of line L. These words, points A and B lie on opposite sides of line L. Well, those words simply mean that points A and B are elements of different half-planes associated to line L. Now it's worth comparing the wording of my version of the plane separation axiom, this wording, with the book's version from page 64. So here's the book's version. It looks similar, sort of if you zoom out. The overall meaning of the version that I printed is the same as the overall meaning of the book's version. But I want to point out some things about the book's version of the definition that I'm not wild about. First of all, the book's version of the definition does not use the terminology of partition of a set. Notice, there's no mention of the word partition. In my version, PSA 1 says, these 3 sets form a partition of the set of all points. That's silly because that terminology of partition should be standard terminology for a course at the level of ours. Furthermore, in the book's definition, the fact that these sets do form a partition, again, it's not mentioned explicitly, but the fact that they do form a partition is conveyed partly by statement I and partly by the start of statement II. So in other words, look here. H1 and H2 are disjoint, and the set of points in the geometry that are not on line L is equal to this union, H1 union H2. Now that's kind of convoluted. Those 2 green sentences together say that L, H1, and H2 form a partition. But it's awkward that that is spread out between 2 statements in this definition. Also, it's awkward, for instance, that it doesn't say explicitly that L, H1, and H2 are all disjoint. Where does that get mentioned? Here it says H1 and H2 are disjoint. What about H1 and L, for instance? Well, if you read this carefully, it says that the points that are in this union, the points that are in H1 or that are in H2 or that are in both, are points that are not on line L. So that means that neither set H1 nor H2 intersects line L. So that means that they're disjoint from line L. This statement says they're disjoint from each other. And then this statement says that all the points in the geometry that don't lie on line L are elements of the union, and then presumably the remaining points of the geometry are the points that do lie on line L. So that's the way of saying that the union of the line and H1 and H2 is the set of all points. So this is a kooky way of writing what could be more simply said, more clearly said, by just saying that L, H1, H2 form a partition of the set of all points. Now here there's a typo. Also, the book's definition does not use the terminology of a segment and line intersecting. To say that the intersection of the segment and the line is not empty could just be spoken as the segment and line intersect. That's a smaller complaint, but these two, I think, make the book's definition a lot harder to make sense of. So for that reason, I will, from now on, only refer to my version of the plane separation axiom, the one presented here 2 pages ago. Now, to actually use the plane separation axiom, it's going to be crucial to be able to do 3 things. First of all, understand the interpretations of PSA2 and PSA3 as conditional statements, and then understand the associated contrapositives for each of those conditional statements, and then finally know how to use a given conditional statement and its contrapositive to prove new statements. So I'm going to talk about that really briefly right now. First of all, consider PSA2. It says each of the half planes is convex. Now, using the definition of convex, we can restate that as a conditional statement, and we can state its contrapositive. Here's the conditional statement version of it. If distinct points P and Q are in the same half plane, then segment PQ does not intersect line L. So that conditional statement is a statement of the fact that the half planes are convex. Now there's a contrapositive version of that same statement. If segment PQ does not intersect line L, then P and Q are not in the same half plane. So these two statements, this one and this one, mean the same thing. They both mean PSA2. Now consider PSA3, which is already in the form of a conditional statement. If P and Q are not in the same half plane, then segment PQ intersects line L. So again, that's already stated as a conditional statement. But realize that there's a contrapositive version of that. If the segment does not intersect line L, then P and Q are distinct points in the same half plane. Now I want to talk about proving statements using given conditional statements and their contrapositives. Suppose that 2 axioms or theorems are stated in the form of conditional statements as follows. Axiom 100 says, if the dog is blue, then the car is red. Axiom 101 says, if the car is red, then the bear is hungry. Now the contrapositives of those 2 axioms would be these statements. Axiom 100 contrapositive would be this. If the car is not red, then the dog is not blue. Axiom 101 contrapositive would be this statement. If the bear is not hungry, then the car is not red. Remember that the contrapositive statements are logically equivalent to the original statements. Now, for example, suppose that we wanted to prove that the car is red. We would have to use Axiom 100. Axiom 100 says, if the dog is blue, then the car is red. So our strategy would have to be first somehow prove that the dog is blue, and then use Axiom 100 that says, if the dog is blue, then the car is red. Use that axiom to justify saying that the car is red. We would not use Axiom 101. Let's look at Axiom 101. Axiom 101 says, if the car is red, then the bear is hungry. That axiom mentions the car being red, but that axiom tells us about the situation where we already know that the car is red. It tells us that in this situation, the bear is hungry. Now, suppose we want to prove that the car is not red. It's important to realize that Axiom 100 does not help us in that case. Axiom 100 ends by saying, then the car is red. Axiom 100 can only be used to prove that the car is red. To prove that the car is not red, we have to use Axiom 101, contrapositive. Let's go back up and look at that. Axiom 101, contrapositive says, if the bear is not hungry, then the car is not red. That's the thing that you would have to use to prove that the car is not red. We have 4 statements here. 1, 2, 3, 4. This is the only one that ends by saying, then the car is not red. So Axiom 101, contrapositive, is the thing we would have to use to prove that the car is not red. Now, what would the strategy have to be? We would have to first somehow show that the bear is not hungry, and then once we know that the bear is not hungry, we could use this axiom to say, well, since the bear is not hungry, we can say the car is not red. So our proof strategy would be to prove somehow first that the bear is not hungry, and then use that contrapositive version of Axiom 101 to say that the car is not red. Here there's a typo. So the discussion above is relevant to your use of PSA2 and PSA3 in proofs. So those statements and their contrapositives are shown here. PSA2 says, if distinct points P and Q are in the same half-plane, then PQ does not intersect line L. PSA2 contrapositive says, if segment PQ does intersect line L, then P and Q are not in the same half-plane. PSA3 says, if P and Q are not on the same half-plane, then segment PQ intersects line L. And finally, PSA 3, this should say 3 contrapositive, says that if segment PQ does not intersect line L, then P and Q are distinct points in the same half-plane. So for instance, suppose that you know that distinct points P and Q are not on some line L, and your goal is to prove that they are in the same half-plane of line L. Well, let's go back up and look at our 4 statements above. Of these 4 statements, there's only one of them that ends by saying, then P and Q are distinct points in the same half-plane. These other statements, this one, this one, this one, all end by saying then something else. Then that, then that, then that. None of those things are the things that we want to prove. Our goal is to prove that P and Q are in the same half-plane. So we have to use PSA 3 contrapositive. So our strategy should be, well, let's go back up and look at PSA 3. PSA 3 says, if PQ does not intersect line L, then P and Q are distinct points in the same half-plane. So our strategy should be somehow prove first that segment PQ does not intersect line L, then use PSA 3 contrapositive to say that therefore points P and Q are in the same half-plane. Now notice we should not use PSA 2. That statement says something about the situation where you already know that points P and Q are in the same half plane. So look, PSA 2 says something about distinct points P and Q being in the same half plane. Our goal was to prove that points P and Q were in the same half plane. So this kind of jumps out at you. There are the words, points P and Q are in the same half plane. But that's not the axiom that we want to use, because that axiom is for the situation where you already know that points are in the same half plane. It tells you in that situation something that we didn't really care about. So since our goal is to prove that the points P and Q are in the same half plane, we have to use PSA 3 contrapositive. So this very careful reading of these conditional statements and their contrapositives, PSA 2 and its contrapositive, PSA 3 and its contrapositive, that is what section 4.1 is largely about, being very careful to pick out which of these four statements you can use to prove something that you need to prove. Now suppose you know that distinct points P and Q are not on some line L, and you want to prove that they are not in the same half plane. Well, let's go back up and look at our four statements. Which of these four statements ends by saying, therefore the points are not in the same half plane? It's this one. Then P and Q are not in the same half plane. That's the only one of these four statements that ends by saying that. So how will we use PSA2 contrapositive? Well, it says if segment PQ does intersect line L, then you're allowed to say that P and Q are not in the same half plane. So our strategy will be first prove somehow that segment PQ does intersect line L, and then use that axiom, PSA2 contrapositive, to say that points P and Q are not in the same half plane. So for example, prove the following. Given a line L in a metric geometry that satisfies the plane separation axiom, claim each of the half planes determined by line L contains a point. So here's the proof. The proof is 10 steps. I've provided the statements, but I haven't provided justifications or illustrations. So that's what we'll do here, and then you'll have a similar kind of problem on your homework. So here we go. So statement 1 is just to state the given stuff. The given stuff was line L in a metric geometry that satisfies the plane separation axiom. So that's what's given, or that's what's stated in statement 1. How do we illustrate that? Well, let's just draw line L. There's our illustration. Now what about statement 2? There exist two distinct points on line L. Call them P and Q. We have to illustrate that and justify it. Well, let's start by illustrating it. Notice in my illustration I've highlighted, by using a different color, highlighted the new stuff. The statement says there exist two distinct points called P and Q, so I drew attention to them by highlighting them in red. All right, now how do we justify this statement? Well, remember that any metric geometry is an incidence geometry, and any incidence geometry is an abstract geometry. And an abstract geometry has to satisfy the abstract geometry axioms. One of those axioms says every line contains at least 2 points. So there's our justification. Again, we use an abstract geometry axiom, which is okay, because remember that every metric geometry is an incidence geometry, and every incidence geometry is an abstract geometry. Now what about statement 3? There exists a point that's not on L. Call it R. We'll start with an illustration of that. So there's my illustration. I've drawn R in red, and I've shown the other stuff that was already there in blue, because it's no longer important. So how do we justify this statement, though? How do we justify saying that there exists a point R that's not on line L? Well, the key is to remember that in an incidence geometry, there exist at least 3 non-collinear points. That's incidence geometry axiom 2. So the fact that there exist at least 3 non-collinear points means that if you have a line, it can't be that every point in the geometry is on that line. There has to be a point that's not on that line. Otherwise, the points would all be collinear. Okay, let's go on. Point R lies in one of the 2 half-planes determined by line L. Now we have to justify that, and then we have to illustrate that. Well, let's illustrate that first. So there's an illustration that shows that point R is in set H1. Now how do we justify this? Well, we are going to have to use something that tells us about half-planes. Let's go back up and look at the plane separation axiom. Here's the plane separation axiom. The key is here. These 3 sets, the line, half-plane 1 and half-plane 2, form a partition of the set of all points. That means that any point that you choose has to lie in exactly one of these 3 sets. Well, we have a point called R, and so it's going to have to lie in one of these 3 sets. Well, wait a second. We know that R is not on the line L, and so that means that R has to be in one of the half-planes. So the justification for this statement that R lies in one of the 2 half-planes is by PSA 1. Now we get to name these half-planes however we want. So notice that we start by saying, well, R has to be in one of the half-planes, so we're just going to call that half-plane the one that's H1. So we put the label H1 on the half-plane that's the one that contains point R. So the justification for this statement is by using PSA 1, and the illustration of that statement is this. Now statement 5 says, there exists a unique line passing through P and R. How do we know that? Well, that's incidence axiom 1. Incidence axiom 1 says that for any 2 distinct points, P and R, there's exactly one line that passes through them. Now, I did not say to illustrate this yet. It's because we need to address something else first. We need to know how we're going to illustrate it. For that, we're going to need this next statement. The statement is, the line that passes through P and R is not L. How do we know that? Well, we know that the line is not L because we know that R is not on L. So since we know that this line that passes through P and R is not L, then it has to be a new line, which we can call M. And so now we're called upon to illustrate this. So we're going to draw the same configuration of points again. So there's my illustration of this new statement. Notice that I have not shown the half-plane because I'm not interested in the half-plane in this statement. This statement doesn't mention the half-plane. This statement only mentions points P and R and line L and the new line M. So I've drawn my illustration in a way that highlights that new object, that new line M. Let's go on. Statement 7 says, there exists a point such that P is between R and that point. So how can we justify that? Well, this is by theorem 3.2.6i. Now, how do we use that? Well, I didn't put theorem 3.2.6 at the start of this video for review, so I'm going to have to put that here in my justification. Given distinct points A and B, there exists a point C such that A dash B dash C, such that B is between A and C. So that's what theorem 3.2.6i says. But we need to say how we're going to use it. We're going to apply it to given points R and P. So this theorem says if you're given points A and B, so that you've got those given points, then there exists a point C that makes this betweenness relationship true. So in our case, our given points are R and P, and this theorem says there exists a point called point that makes this betweenness relationship true. Now, why don't I give that point a name? Well, because I have to make sure that we know how to name it correctly. That is, do we already maybe have a name for it? Well, that's the idea behind step 8. This new thing that I'm for now just calling point, we have to make sure that it cannot be any of our previous points. Well, we know that point cannot be the same as P because this symbol says that those 3 points are distinct points. And by the same reasoning, we know that that thing that I'm calling point can't be R also. Now what about point Q? So how do we know that point, the new thing called point, cannot be point Q? Well, think about it. If that new thing called point were point Q, then that would mean that P and Q were the symbols in that expression. But the thing is, that would mean that R, P, and point, or R, P, and Q would be collinear. So we know the thing called point cannot be point Q, because if that thing were true, if point were equal to Q, then this would be true. That is, this expression where we just replace the word point with the letter Q, and that would tell us that R, P, and Q would all be collinear. But we know that's impossible because R is not on line L. All of that convoluted thinking, all of this stuff, is what goes into saying that the thing called point that's guaranteed by that theorem has to be a new point. And so we have to have a new name for it. We're going to call that new point S. And now we're ready to illustrate. So there's our new drawing showing our new object, point S. Other stuff that's mentioned in this statement are in the drawing as well. I include line M because I need that to convey that R, P, and S are collinear. Notice that I didn't include other stuff in the drawing, though. I didn't include line L. I didn't include the half plane. And I highlighted point S by drawing it in red. Let's go on. Statement 9 says point S lies in the other half plane determined by line L. Now we have to justify that. I haven't said that we need to draw it yet, but we might draw it as part of our justification. We're going to call that half plane H2. Now how do we justify this? Well, here is our first example where we're going to have to use one of those plane separation axiom statements. We want to prove that point S and point R lie in different half planes. So how do we do that? Let's go back up and look at our strategies for showing that 2 points lie in different half planes. To prove that 2 points are not in the same half plane, we have to somehow show that the line segment that connects them does intersect the line, and then we use PSA2 contrapositive to say that therefore the points are not in the same half plane. Well, so observe that segment RS intersects line L at point P, which is between R and S. So we have this picture. And so PSA2 contrapositive tells us the following. tells us that R and S are in different half-planes. So what would be the illustration for that? So the justification for this is by PSA2 contrapositive. So we've shown that each of the half-planes, H1 and H2, contain a point. Let's make an illustration for that final statement. And that was our goal. Our goal was to show that each of the half-planes associated to line L contain at least one point. And that's an illustration of that fact. So you can see that to prove statements involving plane separation involves very careful reading of the PSA axioms and their contrapositives. So in this proof, we used PSA2 contrapositive to say that 2 points are not in the same half-plane. You'll have a similar job to do justifying statements in a proof in one of your homework exercises. Well, that's the end of this example, and that's the end of the video. Thank you.